Okay, so let's imagine that for whatever the purpose, the following function is of value to you. Okay, it models something that you are interested in. Let's say movement of a particle or something to that nature, right? Whatever it is, you and I agree that the function that is graphed to the right is of value to us, some utility. Now, more importantly, you and I agree that what's happening here at point P is really of interest to us. In fact, what we would like to know is how fast this particle is moving at point P. In other words, we would like to know the rate of change, right? Okay, the slope, the instantaneous rate of change at point P. But think back for a second. Think back to all of your training that you know from algebra. All of your training so far requires that in order to find a slope, I would have to give you 2 points. Once I've given you 2 points, it's really easy for you then to find a slope. But now notice that would be the average rate of change between those 2 points. So that's a little bit different than the question we're asking. We're not asking what the slope is between 2 points. We want to know what the slope is at this exact point. Now, how do we proceed? Well, this is what we call the tangent problem. All right, so let me see if I can do a couple things, and let's see if we both agree. Well, since I'm really interested in what's happening at point P, maybe I can even, just for demonstration purposes, let me draw a tangent line. So I would like to know what the slope of that line is. All right, now, so how do we proceed? Well, if we use some of the techniques that we used in algebra, then I would grab some other point on this graph, let's say point Q. And what I'm going to do is I'm going to see if I can find the rate of change between these 2 points. Okay? Now I agree with you, point Q is not of interest to us, only point P is, but let's see if you can follow me. So let me go ahead and I'll save us a little bit of time. I'm going to go ahead and draw a line, at least I will try, connecting point P and point Q. Okay, and now what I will save us time on is if I were to give you 2 points, you could find me the slope. And if you have the slope with 1 point and a slope, you could use the point-slope formula to find the equation of the line. That I'm going to go ahead and give you. So the equation of this line right here is y is equal to x minus 5. Now, the good news is it's pretty easy. My apologies, my little pug is barking in the background, but it's pretty easy to find the slope of a line. So we know that when your equation is y equals mx plus b form, the slope is going to be whatever the coefficient is of your x variable. So in this case, your slope, m, would be equal to 1, right? That's 1x. Now, I want to make sure you follow me through the rest of this, because what have we just stated? Have we just stated that the rate of change at point P is 1? No. What we have stated is the rate of change between the secant connecting point P and Q is 1. But can you agree, you look at the blue dotted line, and then let's look at this highlighted line that I'm highlighting right now. Will you agree with me that if again, thinking of just the slope, looking at the slopes, can you agree that the slope of that blue line is definitely greater than the slope of this secant that I'm tracing out for you right now, right? I mean, you can imagine that if you were climbing a mountain, one of those is a whole lot steeper than the other one. Agreed? All right. So then that that is better than what we had before, which was nothing. But how do we do better, right? Because we want the slope at point P. Well, if this were a classroom setting, I would pose a question to you as, well, what could I do? And undoubtedly someone would say, well, pick a point, right? Right now I'm at point Q, pick a point closer to P. So maybe I choose this particular point. And again, I run, using 2 points, slope, equation of a line, I now have a better approximation than what I had before. Do you see how I could continue to play this game, right? I could keep picking points closer and closer and closer to point P. But can I just move all the way to point P? Well, no, absolutely not. I mean, think about your slope formula, right? M is equal to, let's say, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, the rise over the run. It requires 2 points. If I were to plug in the same point twice, well, then I would have a problem, right? So, yes, I can keep, again, let's think about point P being fixed, and let's think about point Q being able to move, right? So I could continue to move point Q closer and closer and closer and closer to point P, but I obviously cannot move it all the way. We're being quite sloppy in our language, but how close can I move point Q? Well, can I move it I can move it as close as I want, right? For all intents and purposes, the distances between the two could be 0, but not in actuality, right? We need some distance. Just think about the nature of the question. To talk about a rate of change would require some, at least 2 positions, correct? So in other words, I can move it close. I can actually move it the limit as, let's say, delta x approaches 0. Now, wait a minute. Where did this delta x come from? Well, let's say that the delta x represents the distance between point P and Q. So I don't know what that distance is right now, but I think you'll agree with me, as Q gets closer and closer, the distance between them is getting smaller. And in fact, in the limit, I can say that I can let the distance between my 2 points approach 0. Now, what I want you to understand is we will come back to a question like this where we're trying to find the slope, what we would say the instantaneous rate of change at point P. But I want to introduce to you 2 concepts that are separated by, let's say quite a few years of mathematics. So somewhere in high school algebra, you would have been introduced to what's called a difference quotient. And even if you have forgotten all of that, that's okay. We're going to start here. So I will do one of these problems for you. And then it would have been, as of your first couple weeks of calculus class, you would have been introduced to the concept of a limit. Now, for you veteran students out there that have had some exposure to calculus, you undoubtedly probably remember a concept called a derivative. And what I'm here to tell you right now is that the derivative is just the coupling of these 2 concepts. We take the idea of a limit and the idea of a difference quotient. Together is going to produce this function that we call a derivative. But we still need to build a little bit more. So let's start here. So what am I doing right now? Well, right now we're going to go back in time, back to high school algebra, and we're going to practice using this difference quotient. It's also sometimes called a Newton quotient. But let's begin. Okay. So notice what you've been given. You've been given a function. F of x is equal to x squared plus 1, and I've even graphed that function for you here. Now, what I would like to do is I would like to use this Newton's quotient, or this difference quotient, to evaluate this function. Okay, so there's two parts, and again, for those of you that have some are fresh in your training, you know exactly how to go about this. Awesome. Just relax for a second. For those that need a refresher, let's jump in. So there's two parts. The first part is what I'm going to plug into my function, right? So I'm going to plug in an x plus a delta x. All right, now I want you to make sure you understand what it is I'm going to do for the first part. So this x plus delta x is going to be plugged in to this function for x. Are you ready? I'm going to do that right now. So we have x squared plus 1. And as I mentioned, I'm going to be plugging in x plus delta x. Okay, I'm going to make that a little bit smaller. That 1 at least a little bit smaller. So plus 1. Okay, so I want you to understand I agree with you that we still have to clean that up a little bit. But all I want you to understand is the first part is done. That's this part right here. Now, to that we want to minus what? We want to minus the original function. So let's go ahead and do that now. So we want to minus. Now, anytime I use anytime I'm subtracting, I've just trained myself to use some grouping symbols. Okay? So I want to minus what? Well, I want to minus f of x. Well, what is f of x? Well, f of x is given to us. It's just x squared plus 1. So to minus f of x is to minus x squared plus 1. Okay. Now, all of this is to be divided by delta x. Okay. So what happens right now? Well, I'm going to have to FOIL this out, and then I'm going to have to change some signs over here. Okay, so let me go ahead and do that right now. So FOILing that out, so that would be x squared plus, well, x times delta x would be x delta x plus another x delta x. And finally, I would have to multiply delta x times delta x, which is delta x squared. I'm going to go ahead and move this down a little bit so I can give myself some more space. Okay, so what just happened? So, again, if you were daydreaming for a second, here's what just happened. I said I FOILed x plus delta x times x plus delta x. That's what happened. So x times x is x squared. X times delta x is x delta x. There's another x delta x. And finally, there's a delta x squared. Okay, so we still have our plus 1. All right, and now let's go ahead and subtract x squared and subtract 1. So minus x squared, and then minus 1. So minus x squared minus 1. Again, all over delta x. Okay, so some things should start to cancel. This is how you know that you're on the right track. And in fact, the entirety of your function should cancel. So notice how you have a negative x squared here and a positive x squared here, and a positive 1 and a negative 1 here. So let me go ahead and scratch through those, because those are going to cancel out. And then positive 1, negative 1. And I'm going to rewrite this so it's not so sloppy, but I just want you to know that If I have an x plus delta x, and then I add another one, I now have two of them. So I have 2x delta x's. So let me go ahead and write what's left. So I have 2x delta x plus a delta x squared all over a delta x. Okay, so there's we're actually getting close to being done. There's two ways you can think about this. So if you're fairly savvy with factoring and you know that what you can factor and or factoring, canceling, or if you're just good at spotting that you can cancel like factors and not terms, then you might already see that this delta x would cancel this delta x, as well as this delta x canceling one of these delta x's. So if you see that, feel free to jump right to it. If you would like something a little bit more formal, let's pretend like we factor out a delta x out of that numerator. Okay, so we didn't do anything to the denominator. We'll just leave that as delta x. And now let's assume that you and I factor out a delta x out of the numerator. So let's see what's left. Well, if I factor out a delta x from here, I would just have a 2x left over. And if I factor out a delta x here, I would just have one delta x left over. So this would be 2x plus a delta x. Okay, so now you see that these delta x's are going to cancel. And lo and behold, what are you left with? You're left with 2x plus delta x. Okay, let me say a few things. So first off, if I were to, let me speak, if you don't mind, let me speak to that student who has had a little bit of exposure to calculus, okay? So if you have had no exposure, just relax for just a second. So I'm talking to you, student of say a previous calculus class. If I were to ask you, what is the derivative of f of x equals x squared plus 1? Well, would you agree with me that f prime of x is equal to what? 2x? Now, follow me, calculus student, down here, and let's tie this together. Okay, no more thinking about mathematics as recipes for baking cakes. Okay, no more following directions. Let's start to connect these concepts. So notice that the derivative of 2x looks very similar to what we got after using the difference quotient. Only with the difference quotient, we have this delta x laying around. Agreed? Now, what is delta x? I just mentioned it to you a second ago. So we're gonna assume delta x is a distance between 2 points. And what happens if we let delta x approach 0? In other words, what if we just plug 0 in for delta x? Meaning the distance between 2 points is, for all intents and purposes, 0. It's not, but in the limit, it's 0. At that point, if this zeroes out, don't you agree with me that the derivative is what we're left with? So that's what I'm talking about when I say take the limit, couple it with the difference quotient, and that's where our idea of a derivative comes from. Now, let me talk to everyone else for a second. So I want to say a few things really quickly because for your first section, you're going to, there will be at least one, if not two questions on your next test where you will absolutely have to go through this tedious method of finding a derivative. I know you don't like it, for some of, especially if you know some of the quick and shortcuts, but you will have to. So that is what we're going to be practicing for this particular video. But let me make a couple comments as to where students go wrong. So can you imagine if I would not have put these brackets here? I won't erase them because I don't want to confuse anyone, but can you, in your mind, erase those brackets where all we would have is just, let's see if I can do it here. So now you would have negative x squared plus 1. Do you see how a student can make such a simple mistake and how that would alter their answer, right? So if you don't see that yet, your negative symbol, without the brackets, your negative symbol would have been applied to your x squared, which is perfect. But without the brackets, you would not have applied your negative symbol to your 1. So that's one quick thing I want to point out. The other thing is that I need you to understand is when I grade this, what I'm doing is I'm pretending like you and me are having an argument, okay? And I'm following your work all the way through. So it would be okay to have, say, jumped to this step, or my apologies. It would have been okay to have, let's say, have combined these x delta x's right from the beginning. So if you had this 2x delta x here, things like that are fine. But if you were to jump from here to here, then I cannot award you credit, right? Because you're reaching your conclusion in an argument without walking me through all your premises, right? And in this type of argumentation, if I have to agree, then I have to agree with your solution. So show me your steps. Now, the next thing I wanted to point out is for many of you, you remember this difference quotient being here, but instead of a delta x, maybe you had an h here. And if you'd like to use the h instead of the delta x, that's perfectly fine. I'm going to continue with the delta x because it's meaningful for where we're going in this class. I would invite you to keep the delta x, but if you'd like to use the h, that's perfectly fine if that's the way you were trained. Okay, so without further ado, I want you to remember this, okay, because I'm going to grab this 2x plus delta x in just a second. But let's go ahead and go to the first real example. Okay, so what's the task? The task is to find the slopes of tangent lines to the graph of x squared plus 1. So here's the graph of x squared plus 1. But we want to know what the slopes are at 2 points, 0, 1, and negative 1, 2. Okay, so I've highlighted both of those points for you. And before we even start, so what's the goal? The goal is to be able to say that the slope, after we're done, to be able to say the slope of this, the slope of the tangent line to the curve at this point is, and that's what we want to be able to say in just a second. So before we get started, if I had to draw a line that runs tangential to this point, it would look something like this. If you had to take a guess at what the slope of that line is, what would you say? Well, it looks like a horizontal line to me, and I know that the slopes of horizontal lines are 0. So I'm already thinking the slope at this point should be 0. What about the slope at this particular point? Well, I don't know what it is, but it looks like it's, at least I can tell that it should be negative, right? That is decreasing. So I'm thinking whatever the slope is, it should be a negative slope at this other point. So before I go back to example 2, let me now introduce the definition of a derivative. So here it is. So the definition of a derivative of a function. So the derivative of a function at a point at x is. So I'm going to talk a little bit about notation in just a second, But notice, hey, here's that difference quotient. And all we're saying is when all is said and done, take the limit as delta x approaches 0. Now, so this is the definition of the derivative of a function provided the limit exists, right? Because the limit must exist in order to finish that that definition. Okay, so let me go ahead and introduce the notation, some different notations that we're going to be using. So let me start with the most common notation, which is f prime of x. Okay, so f prime of x would mean the derivative of f. The other one that we're going to use a lot is dy dx. The other one, I mean, in other forms look something like this. Y prime would be another notation. Depending on how old your textbook is, you may see notation that looks like this as well. But nevertheless, all of them mean the derivative. I have not, let's agree that I haven't sold you on why you would want to take a derivative yet. So bear with me for a second. Let's practice it, and then we'll come back and I'll try to sell you on the idea of why you would want to be able to do this. All right, so what we want to do is we want to take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That is what we're going to be doing. All right. So the good news is we've already done all of that heavy lifting. So let me go ahead and write the function. So if f of x is equal to x squared plus 1, so I'm going to go back to the previous page. So we did all of that heavy lifting. Let's go ahead and grab this 2x plus delta x. Because at this stage, we're almost done with the derivative, but we still need to take the limit as delta x approaches 0 of what? Of 2x plus delta x. Okay, so you and I assume that you've gone through this part just like we did on the previous page, and now you're left with this final part where you take the limit. Okay, so let's go ahead and, so letting delta x approach 0, that means we can get the distance is what we're talking about here, the width, if you will, is as close to 0 as we would like. For all intents and purposes, it is 0. So I'm going to simply plug 0 in for delta x. So f prime of x is simply equal to 2x. Okay, so now I've defined a derivative for you, but I'm yet to tell you what a derivative does. So it's very important. So let's stop for just a second. So here it is. Here's a derivative of x squared plus 1. But what is it? What does it do? Why do we care? Questions like that. Ready? So first off, I want you to know that the derivative is not a slope. It's not a tangent line. It is a function. So let's write that. So a derivative is a function. So it's a function, and the derivative is a function. It has one job. Well, I don't mean to speak too imprecisely here. Its job is to give you a slope if you give it an x value. Okay, again, that's very sloppy in my language. Let me try that again. So a derivative is a function that gives the slope of a tangent line to a curve at a point. I'll say it again. So the derivative is a function that will give you a slope. A slope of what? A slope of a tangent line to a curve at a point. So let's go ahead and finish this problem. So remember, the 2 points that are of interest to us is the point 0, 1, and then we have the point -1, 2. All right, well, let's go ahead and state the obvious. We have xy, xy. So notice that if you want to know the y value, you would plug x into your original function, right? If you plug 0 into your original function, it would give you the y value of 1. But if you plug that same x value into your derivative, well, let's see what that would be. That would be, let's write it. So f prime of 0 simply means that we're plugging 0 in for x in our derivatives. That's just 2 times 0, or 0. So what did we just do? Well, what did this tell us? It's telling us that the slope at the point 0, 1 is 0. The slope is 0. Now that is kind of what we were thinking, agreed? Remember, at this particular point here, if you were to draw a tangent line, well, that's a horizontal line. We know that the slopes of horizontal lines are 0. So that would mean the slope at every single point on that tangent line is 0. And the only point that these two lines have in common is at 0, 1. So if that is pretty awesome. We were able to find the slope at a point on a curve. Let's do the same thing here. Maybe if you want, you could pause the video. You could try it yourself. But we're trying f prime of -1. We want to know what's the slope at this other point. Notice I'm plugging in the x value into my derivative. So that would be 2 multiplied by -1, or -2. All right, so what we just found out is the slope of this tangent line to this curve has a slope of -2. So m is equal to -2. All right. So now, let me now try to sell you on why you would care. So notice that all throughout algebra, slopes always dealt with lines, right? It would be easy if I were to give you 2 points on a line for you to tell me the slope, right? That's just high school, middle school mathematics. But if you want to know the slopes of curves, right, like what we have, we don't, although a line is a curve, but in essence, if you have some type of curvature, well, it's a little bit different than just finding the slope of between 2 points. So what does a derivative do for us? Well, the derivative allows us to find not the average rate of change, but the instantaneous rate of change. So if you were in your car and you were driving home, it would be one thing to find your average speed. But if you get pulled over by a police officer, right, he would be giving you a ticket because he clocked you at some instantaneous rate of change, some instantaneous velocity, speed that you were speeding, right? Okay, so I think you got it. My apologies for the if that's too much elaboration. But let's go ahead and continue our study. So this is a typical type of question. So what do we want to do? We want to find f prime of x, right? We want to find the derivative for the square root of x. Now, that's part one of the problem. Find f prime of x, find the derivative. After that's done, we want to use that derivative to find the slopes at two different points. Okay, so let's start with the first part. All right, so f prime of x. So at this stage, I can't continue showing you how to use the difference quotient, but I will at least start you off in the right direction, okay? And then I'll give you some pointers. So we have the limit as delta x is approaching 0. Let's go ahead and plug everything in. So this would be the square root of x plus delta x minus the square root of x divided by delta x. All right, now the trick to getting from here or to be able to apply the limit is the same trick you learned in the last chapter where you would have to rationalize. So you would have to multiply by the conjugate, which is the square root of x plus delta x plus the square root of x. So I'm going to write that for you just so you know what you would have to do, and then I'm going to go ahead and get us to the part where we can take the limit. Okay? So here's the part that you would need to do on your own. So that's the conjugate over the square root of x plus delta x. Let me not forget my, well, let's go ahead and finish it. So plus the square root of x. Okay, so I agree with you that I'm being somewhat lazy leaving out this work. In fact, have you noticed that what's interesting about all of this work here is all algebra? The calculus just said, hey, make this term, substitute 0 in for delta x. That's the calculus part of this problem. So anyone who's taught calculus long enough will tell you that the hardest part about calculus is the algebra and the trigonometry, because the calculus is actually fairly easy. Forgive me. So let's now go ahead and get to the part where we can plug in 0 into our limit. My apologies. Okay, so when all is said and done, we would have 1 over the square root of x plus delta x plus the square root of x. Okay, so it's at this stage you finished the difference quotient, and now it's time to evaluate the limit. Okay, so it's fairly simple. We're just plugging 0 in for delta x. Just be careful, you're not plugging in 0 in for x, you're plugging 0 in for delta x. Okay, so if this is 0, that means my denominator is a square root of x plus another square root of x, therefore 2 of them. I have 2 square roots of x's. So f prime of x is going to be 1 over 2 square roots of x. Okay, so this is your derivative. Okay, so this next part's fairly easy. You just want to find the slopes of the graph at the following 2 points. So let me write them. So the 2 points that we care about is the point 1, 1, and we want to know what's the slope at 1, 1. And then we also have the point 4, 2, and we want to know what's the slope at 4, 2. Okay, so it's fairly simple. Just make sure you understand that you're plugging in your x value when you're into your derivative. As of right now, this derivative is it's explicitly defined as a function of x. So right now, let's go ahead. So we plug in a 1. We would have 1 over, this would be 1 over 2 times the square root of 1. And this would be 1 over 2 times the square root of 4. Okay, so f prime of 1 is going to be equal to, well, the square root of 1 is 1, so that's just 1/2. And then finally, f prime of 4, that would be 1 over 2 times the square root of 4, which is 1 over 2 times 2, or 1/4. Okay, so we have answered the second part of the problem. I'm going to go ahead and erase this conjugate so you can see what we just did. So let's take a look at the 2 points of interest. So we have the point here. Sorry, that's not a very good tangent line. Let me see if I could try it again. And then we have another tangent line here. Okay, so the slope of that tangent line is the same as answering the slope of that of the tangent line to that curve at that point. The slope is 1/2. Slope here, 1/4. Okay, now it asks us to discuss the behavior at the point 0, 0. But just understand that, take a look at your derivative, right? If you were to plug 0 in for x, you would have a problem. Now, it's no problem to plug 0, just make sure you understand. Here's your original function. If you plug 0 in for the square root of x, the square root of 0 is 0. So this point is defined on the original curve. But if you were to plug 0 into your derivative, you would be dividing by 0. So, in other words, that last part, it says discuss the behavior at 0, 0. We would say that f prime of 0 is undefined. Okay? Does not exist. Does not exist. Undefined. Null set, however you would like to proceed. Okay. A lot of work. So let me now kind of just that's the last problem that we have to do. Okay, so you need a little bit of practice so you can nail those questions on your test, but I'm going to discuss a little bit more about when your derivative does not exist. So let me start with a statement. So differentiability, meaning that you can take the derivative, okay, of a function. Differentiability implies continuity. So that is an if-then statement. I won't write it as an if-then statement, but if you are if a function is differentiable at a point, or we could say if the function is differentiable, this implies that the function is continuous at these points, right? You could draw, remember we discussed continuity a little bit in the last chapter, but you can draw it without lifting your pen. So I want to make sure you understand. So in mathematics, we have to be careful with if-then statements, all right? So for example, if I were to make a statement like, and if you've heard me say this before, that's, well, you just have to deal with it. But if I made a statement like, if you live in Miami, then you live in Florida, right? That is a true statement. But if I were to switch the if-then portion, right, the antecedent consequent portion of it, and said, if you live in Florida, then you live in Miami, well, that's not necessarily true. Does that make sense? So what am I trying to tell you? I'm trying to tell you that although differentiability implies continuity, the converse of this statement is not true, or at least not always true. And that continuity does not imply differentiability. And the next two examples is to show you that. So I don't need to dwell on this very long. Take a look at the graph. This is the graph of the absolute value of x minus 2. It lets you and I agree that it is continuous. I could draw this without lifting my stylus, right? So it is continuous. But at this particular point right here, it is not differentiable. In fact, if you were to, I'm going to go ahead and you can do this on your own time. If you were to, let me write it for you. If you were to take that derivative, which should be the absolute value of x minus 2 over x minus 2. On your own time, graph the following two. Okay? The original function and its derivative. And what you would notice is that you either have some vertical tangent line, meaning it's approaching infinity as it approaches 2, or you have the limit itself does not exist. You might have a jump. So that's what this example is trying to point out to you, that if you try approaching that or using that limit definition, notice that the limit approaching as you approach 2 from the left is different than if you approach 2 from the right. Right? -1 is not the same as +1. It's not, the limit does not exist at this point when x is equal to 2. I'm going to say that one more time, because if I'm you right now, I'm daydreaming. The derivative exists, or you could everywhere here except at this particular point when x is equal to 2. When x is equal to 2, you can see that the limit does not exist. It's approaching two different numbers, okay, from different directions. So I can actually, if you allow me to, I can sum this up in something very quick, something very trivial, but it would help solidify it. How about this? Derivatives do not exist at sharp turns. Okay, that is very informal. You could say I won't dwell here, but at these sharp turns like this, your derivatives are not going to exist. Okay, so it's differentiable, meaning I can take the derivative of the function, but at 2, notice again, even if you plug 2 into the derivative, you're dividing, you got 0 over 0, right? We have a problem, and the derivative is not, does not exist. It's not differentiable at that point. Same thing here. So if you start off with the function x to the power of 1/3, well, this is the graph of x to the power of 1/3. If you were to walk through and take the derivative, you would get 1 over x to the power of 2/3. What you would find is that if you were to graph the derivative alongside the original function, your derivative would look something like this. Again, do you see how there's a problem when x is at 0? So that's why the statement differentiability implies continuity. If the end statement says if f is differentiable at some x value c, then f is continuous at some x value c. But you can't switch that statement around, okay? So you can find the derivative, you can find the rate of change anywhere you want, except at 0, and you can see this vertical tangent line. So the derivative, which is a slope, a rate of change, right, at to a curve, of a tangent line to a curve at a point, would be a vertical tangent line which would have a slope of being undefined. All right, so I know that was a long video. I hope that was helpful. I will see you guys soon.